Okay, looking at number 5 from the 2015 exam, we're given the graph of the derivative of f. My coffee's ready. They do tell you that f is twice differentiable. We already know it's once differentiable because we're staring at the derivative, but we know the second derivative exists as well. Let's see, f prime has horizontal tangents at -1, 1, and 3. And the areas of the regions from -2 to 1, that area is 9. And from 1 to 4 is 12. And then question A asks you to find where f has a relative maximum. The most common way to show a relative maximum exists is first you want to find critical numbers. And for a relative maximum, you almost always want to show that f prime changes, this is my game plan, from positive to negative at a critical number, at where x equals c is a critical number. Or you can show that f double prime of c is a negative value, because if f double prime of c is negative, that means your function is concave down. And if c is a critical number at that point, then you'll be looking at the maximum. That second approach, the second derivative test, is not going to be used here because we're staring at the first derivative. Although we could use the second derivative test if you wanted. But I'm going to go with the first approach, so I'm going to just go ahead and scratch that out. So first, critical numbers. I want to know where f prime of x is equal to 0, and that happens when x is equal to -2, 1, and 4. And of those 3 candidates, at -2, this is the only place where my derivative changes from above the x-axis to below the x-axis. And so -2 is the location of my local maximum. At 1, the derivative is negative and then negative. So that is not a maximum. We need to go from positive to negative. And 4 is the right endpoint. And we don't have, you cannot have local extrema at an endpoint. So I would say there's a local maximum at x equals -2 only, because f prime does change from positive to negative at x equals -2. And there's your explanation for A. See, B, find the open intervals in which the graph is both concave down and decreasing. So concave down, we need f double prime to be negative. And if f double prime is negative, I want to tie my explanation back to f prime because that's the graph that's given. So if f double prime is negative, that means f prime is decreasing. And if you want f to be decreasing, that means you need f prime to be negative. So I'm looking for places where f prime is negative, which means below x-axis, and decreasing at the same time. And so f prime is negative below the x-axis here. Decreasing at the same time means -2 to -1. That is an interval where this derivative graph is decreasing and negative. And then again from 1 all the way to 3. And so f is decreasing and concave down on -2, -1, union, and concave down on -2 to -1. And again from 1 to 3, because f prime is decreasing and negative on these intervals. There's number B. Moving on to C, I think. There we go. Find the x-coordinates of all inflection points for the graph of f. Now, when I see inflection points, my first thought is you need f double prime to change signs. However, we are not looking at f double prime. I want to tie my answer to f prime. And so let's think what happens when f double prime changes signs. And to make this connection, it's easier to think about, I want to go from f double prime to f prime. That is the same relationship as f prime to f. So let's think about this. If, and this is a thought bubble here, so I'm going to put this in a thought cloud over here. So let's think about the derivative if f prime changes signs. So if your derivative changes signs, that is how you determine that f has local extrema. Okay, so if the derivative changes signs, then f has a local max or a min. If you want to connect that to f double prime and f prime, just add a derivative to each of those functions. So if f double prime changes signs, then f prime has a local max or a minimum. And so that's what I'm going to do here. So if f double prime changes signs, I now am going to look for a local extrema. F double prime changes signs at f prime local extrema, and come down here. That means there are inflection points for f at x equals, and we're looking for local extrema, -1, 1, and 3. -1, 1, and 3, because f prime has local extrema at these points. So you can, for inflection points, you can look for the second derivative to change signs, or you can find local extrema in the first derivative, and that's what we did on this case. Part D, given that f of 1 is 3, write an expression for f of x that involves an integral, then find f of 4 and f of -2. This question, I think it's going to be easier to explain the first question if we go ahead and find f of 4 and f of -2. Now we are given some initial condition, and we are given the derivative of f. And so if I want f of 4, I'm going to leave a little bit of space because I'm going to come back up and I'm going to write an expression for f of x up here. So f of 4 would be my initial condition plus the area from 1 to 4 of f prime of x. Well, this is going to be fairly easy to do because f of 1 is given, and in the paragraph they tell you that the areas from -2 to 1 and 1 to 4 are 1 and 12. And so the area from 1 to 4, well, you have to remember that this is below the x-axis. So while the area is 12, the definite integral will have a negative value. So it's 3 plus -12 would give you a value of -9 for f of 4. And then we'll do the exact same thing for f of -2. F of -2 is going to be f of 1 plus the integral from 1 to -2. And it is okay to go from right to left. Nothing wrong with that. You just have to remember that that is a negative direction. So f of 1 is 3. The area from 1 to -2. Now, this region is below the x-axis, and we are going from right to left. That is 2 negatives. So we will add that area of 9 to get a final area of 12. So there is f of 4 and f of -2. And what we did, f of 4 was f of 1 plus 1 to 4 of f of f prime. F of -2 was f of 1 plus 1 to -2. So then f of x, we're going to do that exact same thing. It's going to be f of 1 plus the area from 1, and we're just going to put the x up here. And you may be thinking f prime of x dx. However, you are not allowed to have the same variable in the antiderivative. You cannot have a dx antiderivative with an x for the limit of integration. So the only thing I have to do to adjust my f of x expression is I have to use some other variable here. Does not matter what you use. Typically, people use t, so I will use a t. And so there's my expression for f of x, and that would be sufficient to finish answering the questions. My little pickiness, I don't like the inconsistency that my f of x is 1 to x and it's f prime of t dt, and these are f prime of x dx. So I'm going to go back and change these two x's. You don't have to do that. There's nothing wrong with those. This is just going to make me a little bit happier having the t's here instead of the x's. And the fact that this is an x-axis and this is a f prime of t does not influence the value of those integrals. So there is no problem with that whatsoever. And that is all for number 5.